So in this last example, we are going to have to determine if a vector is in the span p1 of x, p2 of x, given that p1 of x is x minus 4 and p2 of x is equal to x squared minus x plus 3. And we have to see if this p of x function is in or spans p1 of x and p2 of x. So here is a little bit different. We're dealing with polynomials and we have to put this in vector format. And so the way we can put in a polynomial in vector, it kind of depends on how you want to do it, but you pretty much have to put in the constant on each row, and then each row represents a different, I guess, function. So what I mean by that is, so for p1 of x, we're just gonna rewrite it in a different color. So p1 of x can also be written as 0, 1, negative 4. So our 0, this is our x squared, this is our x, and then this is our constant. But you could also write it as negative 4, 1, 0. So this is another way of writing this. It's pretty much flipped. So this is your constant x and this is your x squared. So either one works. The only thing that you need to keep a close eye on is the consistency. So if you have, in the sake for this example, if you have p1 of x is equal to this, then that means p2 of x must also be in that same format of the x squared, x, and c. So that would be 1, negative 1, and 3, since it's still x squared, x, and c. So that's the only thing you have to keep your eye on or be aware of, that you just have to be consistent. So like I said, it doesn't matter what way you do it. Either way is right as long as you're consistent. So if I were you, I'll just probably pick one and then just stay with it. And then that way you don't have to worry about if you're doing this right or if you flipped it. As long as you're just consistent, you should be fine. So now that we put P1 and P2 in matrix, we also gonna put on the last one in matrix format. So that would be 2, negative 1, negative 2. And so to check if it spans, we're gonna put this all in one not vector, matrix. So it's gonna be P1, P2, and then P of x. So you'll have 4, 1, negative 4, 1, negative 1, 3, and then 2, negative 1, negative 2. And so this is where it becomes interesting to check if it spans. So where you're gonna end up, or what you're gonna have to do now, is you're gonna have to put this matrix in row reduced echelon form, and then the results will tell you if P spans P1 and P2. So we're gonna go ahead and do that, and then I'm gonna explain what happens with your end result. So we're gonna get started with I guess we can just switch the first. Yeah, first. And fourth row. Yeah. First and fourth row will be switched. So R1, R3. And so you're just left with negative 4, 3, negative 2, 1. Second row stays the same. And 0, 1, 2. All right. And then we're going to switch the second and first row so we can have the leading 1 already present in the first row. And so you'll have 1, negative 1, negative 1, negative 4, 3, negative 2, 0, 1, 2. So now we can start actually simplifying this. So what you can do is you can erase this. You can take out the 4 here just by adding the first row multiplied by 4. So R2 plus 4R1 is going to equal to your new R2. And so that will give you 1, negative 1, negative 1, 0, 1, 2. And then this would be 0. 4 times negative 1 is negative 4, plus 3 is negative 1. And then negative 4 minus negative 4. Negative 2 minus negative 4 is equal to negative 6. Alright, so now we're just going to add row 2 and row 3 together to get a new row 3. And that will be 1, negative 1, negative 1, 0, negative 1, negative 6. And then we have 0, da, 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 0. And then negative 6 minus 2 is negative 4. Hello, and this is a different video. Apparently, this portion of the video is just kind of cut off. So I'm gonna just go ahead and continue it from here. And so lastly, we were able to get the second row to be 0, 1, 6. And so now what we can do is get rid of the 1 in the first row, or the negative 1 in the first row, and then change this negative 4 to a 1. So we're just going to have to multiply negative 1 over 4 on R3, and that would just be our new R3. And then we'll have R1 and R2 summed together, and that's just going to give us our new R1. And so when you do that, you'll get 1, that's not a 1, 1, 0, 0, then 0, 1, 0, and then 6 minus 1 is just 5, and then this would be 6, and this would be 1. So right here, at this point, you can reduce the matrix to 1, or to have a diagonal of 1s, because you can just use this one to get rid of the 5 and the 6. So I'm just gonna skip it, or skip that portion, and just put this in this final row reduced echelon form. And so we're just gonna have a pretty much an identity matrix. And so here's how you can tell if this is, or if it spans in the matrix. So when you have it in row reduced echelon form, what you're gonna look for are the pivots in the matrix. So right here we have a pivot on column 1 and column 2 and column 3. So the number of pivots, so if the number of pivots is equal to the number of columns, then that means our P of X doesn't span P1 and what is it, P1 of x and P2? So it's P1 of x, and I'm just gonna take out the x. P1 and P2. And the reason is because when you have a matrix in, well, in this case, when you have this in row reduced echelon form, we can see that the third column, or I guess third row, third column, it contains a pivot. So that means that it is linearly independent from the other two pivots. So in this case, it'll be P1 and P2. And what that basically means is if you can't write the P of x as a linear combination of P1 and P2. So there's no A nor B such that when you, or scalars A or B such that when you multiply them with P1 and P2, you cannot get the P of x that we were looking for. And so, in contrast, to tell if it does span, this will span if the number of pivots is equal to the dimension of the span. So for our span, we have P1 and P2. So that means the dimension is equal to 2, so 1 and 2. And so what we essentially want is to have a matrix that'll be 1, or having 2 pivots. So we have one pivot here, and then we have the other pivot on here. And so the number of pivots is equal to the dimension of the span, or basically the number of vectors in the span. Then the vector that we're looking at, or we're trying to find, is in the span of the vectors provided. So if we had an answer that gave us this matrix, then that means P of x spans P1 and P2. And that is pretty much it for this example. So I will be seeing you guys in another video.